This is CPM Calculus, Chapter 4, number 26. So here we're given a little history lesson. Georg, Friedrich, Bernhard, Riemann. Riemann, yes, this is our famous Riemann sums guy, right? He was born in 1826 and died in 1866, so he only lived 40 years or so. So he formulated the modern definition of an integral, right? Because we know we go from sigma to integral by taking the limit as n goes to infinity, right? When n is the number of rectangles, right? Over here. Anyway, he decided that it was not absolutely necessary that each rectangle have the same width. Okay, so we know when we're looking for the area under a curve, we find the width of each rectangle. Well, these are bad rectangles. But the width we know is just b minus a over n. And that's equal, right? That's going to be the base for every rectangle, right? Rectangle. But he said that they don't need the same width. Not absolutely necessary for the rectangles to have the same width. And then he said they do not even need to be the same type, right? So some can be a left endpoint, some can be a right endpoint, some can be a midpoint rectangle, right? In fact, some can be trapezoids, maybe he was saying, but that's not what it says here. Anyway, but for example, examine this graph here, all right? If you look at the graph, we have rectangles of varying widths. This rectangle has a width here that's much larger than these rectangles here. This rectangle has a width that's smaller than this one, right? So all the widths of the rectangles that we're using to kind of estimate the area under the curve from A to B are different, right? So will they still give a good estimate of the area even though the rectangles do not have the same width? So even though the width does not follow this pattern, right? The width is different. Will this still give a good estimate of the area under the curve? And look at it and tell me. I mean, I see that it's going to be like an overestimate here, over here, well, over and under again, right? I see that this is basically the same kind of estimates we're making when we do have an equal width for our rectangles. So just estimating the area underneath the curve, it doesn't look like the rectangle width matters, right? We can use small rectangles here, a big one here. I mean, it might give us a better or worse approximation, but it's still going to give us a good estimate of the area. So will this give us a good estimate? Yes, it will, right? We still get an approximate area if we do not use the same width for each rectangle, right? Because this pretty much looks like a good approximation for the area, all these rectangles, for the area under the curve from A to B. When we add up all the areas, we still get a good approximation of the area. So will they still give us a good one? Yes. Okay. So if you still have questions about this problem, let's talk about it in class. Ask again. But this is basically asking you to think about approximating the area under the curve. Does a consistency of the rectangle width really matter? If these were all big rectangles like this one, the width, it might be like this, or if we use left endpoint like this. But basically, changing the width to varying degrees still gives a good approximation of the area. All right, so that's going to end looking at CPM Calculus Chapter 4, number 26.